So let me start by thanking the organizers for giving me this opportunity to speak here. So I'm actually from ENS, and it's really a great honor to be here to be able to present this work. So what I want to tell you about today is this program that we propose and are currently developing together with Martin Kruczynski, where we try to solve the low energy, strongly coupled physics of gauge theories like QCD and have obtained some exciting results. And the style of the work might be a little bit unfamiliar to most of you since it will be non-perturbative and also mostly numerical. But I'm going to focus on mainly present the idea of the program with a minimal amount of technical details. Let me start with the basic motivation. We consider asymptotically free gauge theory with NF massive quarks that undergoes chirosymmetry breaking and confinement. The theory is described by this QCD Lagrangian and is parameterized by a set of numbers. And a long-standing question is to understand what is the low energy physics of this theory. Due to chirosymmetry breaking, the low energy physics is dominated by the pseudo-Goldstone bosons. And in the case of two quark flavors, these are the three pions. And one can write down an effective Lagrangian to describe the pion physics that is parameterized by the mass of the pion and the f pi. This theory is, however, not renormalizable, and the effective field theory approach is to add infinite many terms with unknown coefficients. And in chiroperturbation theory, these coefficients are determined by fitting with experimental data. But of course, in principle, we should be able to compute them from the underlying UV gauge theory. So here's the problem that we're facing. We have a theory that at high energy is described by weakly coupled quarks and gluons, and it's controlled by perturbative QCD. At low energy, it's described by weakly coupled pions. There's an effective field theory framework. This effective field theory will, however, break down at some energy scale, which is much lower than the energy scale that we have perturbative QCD control. And in the middle, we have this gap of strongly coupled regime that we have no control. To solve this problem, we propose a gauge theory bootstrap approach that allows to bridge this strongly coupled gap and connect all three energy regime, and also allow to compute strongly coupled dynamics like amplitudes, form factors, and couplings and the spectrum. The rules of the game is the following. We're going to assume chirosymmetry breaking and confinement. These are important properties of QCD that we eventually want to be able to prove, but for the moment, we're going to use them as assumption. And we're going to use as input the defining parameters of the gauge theory, and for the moment, two additional low energy, universal low energy parameters, the mass of the pion and f pi. It will be important for the future to see if we can also compute these last two parameters from the gauge theory parameters, but for the moment, we're going to use this input. And it's worth clarifying that this is a theoretical and numerical computation in the sense that we're not using any experimental scattering data as input. Before I describe the approach, let me give you a summary of the basic building blocks of this approach. Let's do this by looking at the complex plane of the Mandelstam S variable. The center part of this approach is a modern S-matrix bootstrap technology that allows to do a non-perturbative parameterization of the scattering amplitude that encodes a set of generic consistency conditions. And below the two particles threshold at a very low energy region, we're going to use as input the tree-level amplitude of pions. And above some energy scale that is large enough that we believe perturbative QCD works, that we call S0, we're going to use some conditions from perturbative QCD, namely the SVZ sum rule and the asymptotic behavior of the form factors. Basically, the idea is to look for scattering amplitudes and form factors that satisfy a generic set of consistency conditions like analyticity, crossing, and unitarity, and in the meantime, match at low energy behavior that's predicted by chiral symmetry breaking and at high energy perturbative QCD. So we're going to perform a test of this method with NF equals to 2, NC equal to 3 for the purpose of comparing with experiments. But these are gauge theory parameters that are changeable in the approach for a generic study. So let me start with a brief review of the modern S-matrix bootstrap technology. We consider 2-to-2 Pion scattering, and the T-matrix element give a non-perturbative definition of the scattering amplitude. The scattering amplitude satisfies some consistency conditions. First, crossing requires that it's invariant under the TU exchange, and analyticity requires that it's an analytic function in the Mandel-Stam invariance with cuts for STU larger than 4. Here and below at many places, I've taken mass of the pion to be 1 to set a unit. And also we have an on-shell condition. These consistency conditions can be automatically encoded into the so-called Mandel-Stam double dispersion relation. So the scattering amplitude is non-perturbatively parameterized by the double spectral density here. And in the numerical computation, we'll discretize these double spectral density, which are our bootstrap variables. Further constraints come from the following consideration. If we go to the amplitude with a fixed SU2 isospin and then define the partial waves, these partial waves are analytic function in S with a cut from 4 to infinity and 0 to negative infinity. Notice that first in the so-called unphysical region for S between 0 and 4, the partial waves are real. And so these are actually some linear functionals of the bootstrap variables. And in addition, in the physical kinematic region above the 2-particle threshold, we can define the inelasticity and phase shift this way, which are experimentally accessible quantities. So the unitarity constraint then requires that the modulus of S, this S is smaller than or equal to 1 for physical values of Mandel-Stam S, any angular momentum and isospin. And notice that this can be written as a positive semi-definite matrix like this. And since the space of positive semi-definite matrices is a convex space, so unitarity constraint defines the convex space of allowed scattering amplitude, which allows us to use the powerful tool of convex optimization to study scattering amplitudes. So the modern perspective is the following. We have a space of generic amplitudes satisfying these consistency conditions, which you can also think of as a space of constrained bootstrap variables. And we can then start from a setup that encodes all these conditions, maximize some linear functional of the bootstrap parameters to reach the boundary of this allowed space of amplitude. In the S-matrix bootstrap program, this functional is usually chosen as some physical quantities that one wish to put a bound on. But for our purpose, this point is not particularly important. What's important is that once we're at the boundary, there's a set of extremal bootstrap parameters which allow to reconstruct some extremal amplitude sitting on the boundary. So in this sense, the maximization serves as a tool to obtain some non-perturbative numerical computation of the scattering amplitudes. To give you an example, we can consider 2 linear functionals that is the partial wave evaluated at some unphysical point, and then plot some 2-dimensional projection of the space, infinite dimensional space of scattering amplitude given by these constraints. We'll obtain a shape like this, which is convex. And at each of these points, there is some extremal numerical amplitude there. It might be a little bit confusing what this functional means. For us, it doesn't have specific meaning. We only use them as a numerical tool to be able to access some non-perturbative computation. And as we'll see, we're going to include the information about the theory we want to solve to shrink this space to very small. That brings us to the next step where we're going to put in some low energy information. Chiral symmetry breaking says that the Goldstone boson are weakly coupled at very low energy. If we look at the tree level amplitude, it's a linear function in the Mendel stem S. And correspondingly, the partial waves are also linear in S. And this gives a very good description in the very low energy unphysical region below the 2-particle threshold. So in the bootstrap, we're going to require that the partial waves in the bootstrap to match this tree level partial waves in this very low energy unphysical region. And I'm not going to describe the technical detail of how this match is done. But once this is done, we look again the projected space of amplitude, and it quickly shrinks to a very tiny region that supposedly include the amplitude that describe weakly coupled Goldstone boson scattering. So let's zoom in to look at some detail of this. Here I'm plotting half of this convex shape, which is, again, at each of these boundary points, there's an extremal amplitude there. And I also plot a straight line here, which is the tree level amplitude evaluated for these two linear functionals for different values of f pi. And the black dot there corresponds to the f pi equal to -2 MeV. And so at this point, it's natural to identify a point on the boundary that's close to the 92 MeV point, and we want to look at the extremal amplitude at this point, in particular, what kind of phase shift we get in the physical region. And this is the point that will use the value of f pi. So the results are shown in these three plots, where I'm plotting the phase shifts for S0, S2, and P1 as a function of the center of mass energy. And let me specify that since this is a numerical computation, so what I'm plotting in these magenta points are discrete numerical evaluation of some analytic function. And for comparison, I also plot experimental data on this phase shift. We can see that with this simple low energy input, the S0 and S2 wave already look quite like the experiment. In particular, the S0 wave has this kind of rise that should be identified with the sigma meson. And note that in the experiment at around 1 GeV, there is a big jump, which corresponds to the kaon production, which we don't expect from a 2-flavor quark model. But the feature of QCD, which is the row resonance that's in the P1 wave that we see in the experiment, does not appear. And this also makes sense since we haven't given any UV information yet. So at this point, the bootstrap has no idea that QCD is the theory that we're trying to solve. That brings us to the final step, where we're going to input the information about QCD. To do that, let me first describe an important development in the S-matrix bootstrap that includes the form factors. In addition to the 2-particle asymptotic in and out state, we can consider a state that is created by some UV local operator. The matrix that describes the overlaps of these states has to be positive semi-definite that arrives from the unitarity of the theory. So we see that the upper left corner here is exactly the 2x2 positive semi-definite matrix we see before. But now we have two additional functions. The first one is the 2-particle form factor, which is an analytic function in S with a cut from 4 to infinity. And we can non-perturbatively parameterize it using the imaginary part across the cut. And the second one is the spectral density of the 2-point Weidmann 2-point function for the local operator, which has a support at S larger than 4. So we see by including these two additional functions, we have extended the bootstrap variables. And the important point is that now we are able to connect with the UV theory. What we would like to do is to connect with the UV gauge theory, and we'll have such a positive semi-definite matrix for each physical value of Mendel stem S, angular momentum, and isospin. And the idea now is to construct operators from gauge theory with desired quantum numbers such that their form factor and spectral density enter this kind of matrix. To take an example, we can consider the vector current that has isospin 1, angular momentum 1, and we can directly write it down using the quark fields. And taking the Fourier transform of its time order 2-point function, we get a vacuum polarization, which is which is an analytic function in S with a cut from 4 to infinity. And the discontinuity across the cut is the spectral density. Now comes to the key point. When we're at a large space-like momenta, we're in the asymptotic free region, so the vacuum polarization is controlled by perturbative QCD. And to do that, we will use the famous SVZ expansion. The idea is that we take the OP of the local current and insert it into the vacuum. Then we get the following short distance expansion of the time order 2-point function. Note that since the vacuum here is a symmetry breaking vacuum, more than the identity operator has non-vanishing contribution, which includes the quark and gluon condensates. And the coefficient in front is completely controlled by perturbative QCD. After doing the Fourier transform, we then get a large S expansion of the vacuum polarization, which in the case of vector current take this form. We can see how the gauge theory information are contained on the right-hand side. Now, the final step is to connect this perturbative QCD region with Bootstrap at some large enough energy scale S0. And the idea is to consider the contour integral of S to some power times the vacuum polarization along this red contour here, which is supposed to vanish due to the analyticity and by Cauchy theorem. And so the integration on the big circle becomes the right-hand side, where we can use the SVZ expansion since we believe the perturbative QCD applies there. And the integration wrapping around the cut in the low energy region becomes some moments of the spectral density. So we see how the gauge theory information contained on the right-hand side becomes some linear constraints of the Bootstrap variables. Again, take the example of vector current, we get the following finite energy sum rule. Notice that the condensates are suppressed at large S0, so we're not really using it as an input, which is good since we don't know how to compute them anyway. And finally, perturbative QCD also provides some control for the asymptotic behavior of the form factors. Again, take the example of the electromagnetic form factor. People have computed a long time ago that at large momentum transfer, it has this kind of decay, and this can be computed perturbatively. And in the practical numerical implementation, we simply require that beyond the energy scale S0, the form factor is very small. And how small? This can be estimated using this kind of expressions. So that's everything about the approach. And let me show you the test. We have done 2 tests. First one taking S0 around 1.2 GeV, and the second one 2 GeV with a set of parameters like this. For each case, again, we identify a point on this kind of shape close to the FPi tree level point. For 1.2 GeV, now I'm plotting again the phase shift for S0, S2, and P1. S0 and S2, as before, have a good agreement with the experiment, but now we see that in P1, there's also a row resonance appearing, and this clearly comes from the information of the UV theory. Further going to 2 GeV, we can see more things. Here I'm showing the phase shift for the first 6 partial waves as a function of the center of mass energy. And so in addition to the row 770 in the P1, we see more things. For example, in the spin 2 sector, we have a rise in the phase shift that should be identified with the F2 meson. And there's a reasonable agreement with the experiment. And at P1, at a slightly higher energy, we also see another phase rise, which should be, for the moment, we identify it with the row 1450. It's also interesting to see that we have obtained some small amount of particle production. Here I'm plotting the inelasticity, which is at around the energy that resonance are produced, which is also in agreement with what we see in experiments. Okay, and with these results, thank you. Now we can do many analyses. The first one is we can do a low energy threshold expansion of the partial waves to extract scattering length and effective range parameters. We get this set of parameters from the bootstrap, which has a reasonably good comparison with phenomenological determination over the years. And the same thing, we can do it for the threshold expansion of the form factors. And to extract the Pion charge radii, this bootstrap determination for scalar and vector form factor also has a good comparison with the experiment. It's interesting to see that with this set of threshold parameters, we can now actually calculate the Cairo-Lagrangian coefficients. And here I'm showing the comparison with the phenomenological determination, which I think is also reasonably well given the small amount of information we put in. In the P1 wave, the rho 770 meson appears as a second sheet pole in the partial wave. And from the bootstrap numerical result, we can actually plot this pole and extract its location to compare with PDG. And going into the vector form factor, the dots here shows the numerical result on this, and we can fit it with the Brad-Wigner form or the more involved Gunarius-Sakuri form to extract the mass and the width of the rho meson and further the rho pi coupling and compare it with the particle data group again. It's interesting to notice that when we go to the 2GeV, the vector form factor has a small bump at a higher energy that we already identified with the 1450, rho 1450. And this is actually the leading meson of the second Regge trajectory. So we see that the bootstrap result has uncovered the leading mesons in two different Regge trajectories. To obtain the rest, we need to improve the numerical precision and to see what happens. And finally, in the spin 2 case, this is the gravitational form factor where we have the F2 meson, and we can do the same thing. So let me conclude. We propose a gauge theory bootstrap approach, which is a theoretical and numerical computation that uses as only input the gauge theory parameters and for the moment, 2 additional low energy parameters. It allows to compute the strongly coupled low energy physics of asymptotically free gauge theories. And the numerical test with NF equals to 2, NC equal to 3 find good agreement with experiments. The results suggest that we might be on the right track for solving QCD or gauge theories in general. And let me stress that the computation is really fast with machine precision. It takes about 20 minutes on an average laptop to produce these plots I showed. And we have made the computational program completely available. It would be really nice to have further refinement and improvement to make it more robust. For the future, there are so many things to do. For example, we can start changing the gauge theory parameters in this input to see how the low energy strongly coupled dynamics depend on that. There's also an interesting interplay between the chirodynamics and the gauge theory, as we see earlier that the S0 wave arises simply from the chirodynamics, while the P1 wave that contains the rho meson comes from QCD. And we have already started doing some of this exploration, for example, changing the NC with a fixed tooth coupling and to examine, for example, in the S0 wave, what happened to the sigma meson. Here is some really preliminary result, but we start to see that as we increase NC, the sigma meson becomes sharper and sharper as one expects for a typical QQ bar state. And finally, further down the road, it would be really nice to have some analytic understanding of our approach. Given the expertise of this audience, I would like to suggest that perhaps what needs to be understood is the convex geometry that's defined by these generic consistency conditions of analyticity, crossing, unitarity, plus the perturbative QCD constraints. Since we have seen that the strongly coupled amplitudes of the physical theory of strong interaction can be attained this way. in any case, it would be really nice to further develop this framework and have a deeper understanding of gauge theory. I will finish here. Thank you.
Thank you very much for that impressive talk. Maybe I can ask one question just to kick things off. Have you considered comparing to lattice gauge theory? Because they can do 2 to 2 and change parameters and so on.
Yes. For this NC exploration that we start doing, it will be definitely good to compare with lattice gauge theory. But as far as I understand, they haven't done much with, I mean, I don't know a lot about lattice gauge theory, but yeah, it will be nice. I hope
they could turn off strange quarks, for example. So you could see if certain small differences are due to the fact that the strange quarks are in or out and so on.
Yes, definitely.
Hi, I have a question. So I'm actually a little bit confused why you have to input the UV form factor to get the rho resonance. Because people also do the large N chiral perturbation theory bootstrap. And in that case, they only input, the asymmetrics and latticity and unitarity without inputting any form factors. And in the exclusion plot of L1 and L2 on the boundary, they can find some rho peak in the extreme amplitudes.
Which work are you?
It's like by the Jan Albert and Irando Rastani. And could you explain why is that?
As far as I understand, they have used the rho mass as an input in their
no, they have the exclusion plot, and there is a line corresponding to Skirm model. And if we look at the extreme amplitude there would be showing a peak at P wave.
Okay, I've seen their paper, but I didn't see this kind of plot for the P1 wave, so I'm not sure. As far as I understand, they have to use the mass of the rho, but maybe we can discuss later about this detail.
Okay.
Thank you for your nice talk. I have a naive question for this picture. If you take the NC is very large, what's is the asymptotic behavior of this? I mean,
for the phase shift.
Yeah, just.
Well, I mean, here I'm just showing the phase shift that correspond to, like, as you increase the NC, it's like a narrow resonance. So in general, it just goes from 0 to pi. Unless there's some other resonance that's at a higher energy, it will go to another multiple of pi.
Okay, thank you.
Hi. Hello, on this side.
Oh, okay.
Thanks for the nice talk. I was wondering, because there were some work previously also done by Bootstrap, inputting only the low energy data in the form of Adler zeros by Guerrieri, Penedones, and Vieira to span the space of scattering lengths, which values are allowed and which values are not. Do you think it will be interesting to check inputting the UV behavior, how much further you can squeeze this space, or did you make any comparisons between your data and this way of constraining the scattering lengths, for example?
Okay. I guess one thing one can do is to use the UV information, but to check some, to consider some functionals that's the low energy parameter to see how narrow range that we get.
Yeah, because one can isolate how UV actually affects the final spectrum or scattering lengths or whatever observable you are trying to bound or trying to find, right?
Yeah, we're not trying to bound anything here.
Okay.
We're trying to use this thing about maximizing some functionals just as a tool. We're trying to identify the low energy physics of a specific UV theory. And yeah, that's the idea.
I see. Thank you.
Can I ask one more question?
Yes.
Are you able to read out this exclusive Pion form factor? You used a loose bound on it as part of the input.
Yeah, so I think the idea here, I mean, I think there's so much perturbative QC information that we could exploit right now with these. For the moment, we're only using the very simple thing that is very small at higher energy. So maybe one thing to do is to see whether it really has this kind of behavior as a result.
Yeah.
But yeah, that's one direction that we should look at.
Yeah,
yes.
that would be great to see because I've looked at, or these calculations get large perturbative corrections. So
Yeah.
while the scaling looks good, the magnitude is hard to get accurately, I think.
Yeah.
Okay, let's thank Yifei again.
Thank you.
Great talk.